Hi, we're Team 21, and today we're going to be talking through our analysis and deli meat slicer. Deli meat slicer cuts large slabs of meat and other foods into thin slices. It does this by placing the meat or food over a blade, which slices and shears the food. We anticipate the production volume to be 75,000 units split up between our primary and secondary customers. Looking at an exploded view of the deli slicer, it is all based somewhat around the base, where the blade, guard, blade cover, and then the actual sliding plate sit, which is where the meat will then cut and fall onto the base, having passed over the blade. Handles and legs are all features that support the function of this actual deli slicer. Looking at our customer groups, we have the main primary customer group is anyone in the food industry, restaurant owners who will use the deli slicer to provide food to customers. And the secondary customer groups is at-home cooks or any individual who is using their deli slicer for themselves. Looking at the functional analysis, the main function is to slice meat. In order to do that, it must both cut meat and guide meat. To cut the meat, it must hold a tool and apply a force with the tool, both allowing translation and rotation depending on what tool is chosen. In order to guide the meat, it needs to move it and hold it, which needs to maintain its position, prevent slip. We also need to have dependability in order to prevent cuts and other senses and enhance the product.
The next thing that we completed were two separate fishbone assembly diagrams. The first assembly sequence is a bottom-up assembly, where the base panel is mounted to a fixture and then all of the parts are fastened onto the base. The second assembly sequence is much more of a sub-assembly focused. The base is still mounted to the fixture first, and then all of the important sub-assemblies are built up and attached one by one. After we had these completed, we then scored each sequence in the table shown based on how we thought they would perform in the categories that are shown on the left. We scored them from 1 to 3, with 1 being the worst and 3 being the best. The subassembly sequence, or sequence 2, ended up being the best due to its advantages in testing and assembling the subassemblies in parallel.
Our function component mapping matrix can be seen on this slide. It shows which product function is realized by which component. The components are taken from the fishbone diagram, while the functions are taken from the FAST diagram. Each function is realized by at least one component, and each component realizes at least one function. Aside from that, no function has more than 40% of the parts performing it, which means that we do not have to go back to the FAST diagram, and we can move forward with our current design.
All right, here is a look at our bill of materials and our rough cost estimation. Processes for any given material throughout here are mostly given. Same with the material itself, and the low carbon steel is FDA approved a non-toxic metal, so it is safe for food to be on this product for consumption. We are looking to outsource the blade, any fasteners or screws, and the motor for this meat slicer. And the overall price at the end of the day for making one of these is just above $85 per part. Looking at the quad chart, we are looking to either redesign or consider elimination for any part that was deemed low importance or high cost in order to save on the assembly time and the overall cost of the product.
For our functional differentiation and component commonality tables, are listed here. We have the functional differentiation table, which compares our primary and secondary groups. We decided that allowing safety and reliability is important for both, while minimizing noise and enabling portability is probably something only the secondary customers are going to need, since our primary customers are primarily in the industrial space, and noise and portability are not as crucial as they will be in a fixed position. And then for our component commonality table, we have differentiated between platforms and modules, platforms being the more essential pieces and common between both variants. We have the base, blade, and backplate, and then the modules are the less essential, lower cost, which include legs, which minimize noise, the sliding handle, and the blade cover. For the assembly sequence, we have the original listed above and our variant below. We have optimized this assembly sequence by combining the blade cover and guard, which reduces the amount of steps in the sequence. And then we delayed the differentiating module to the last assembly step to increase the ease of production.
One common interface that can be seen comes from our first variation, which is adding a locking mechanism to prevent the sliding bracket from sliding by itself. The knob slides into the base and twists to lock into place. This differentiation will mostly be used by our secondary customers since they'll be moving and storing it by picking it up and putting it in a safe location. Most of the design stays the same except for the sliding handle, the slide bracket, and the base, which take minimal variations.
And here for our product variation with our original product on the left and then our variant on the right. We show here the differentiating factors, which include a handle cutout in the base to increase ease of portability, the locking mechanism in the sliding handle, and then we have shown the blade cover and guard to be combined into one piece.